Welcome to topic 10.1. In this topic, we are going to define what is a solution. So we are also going to work on some terminology and distinguish a solution, suspension, and colloid. Oops, let's see. It's got put upside down. Let's try this again. So a couple of things to start with. This is going to be review of terminology that you've seen before. Mixtures are a category of one of our mixture type. And so heterogeneous mixtures are ones in which the material that makes it up are not uniformly mixed, as where a homogeneous or homogeneous mixture is uniformly mixed. Aqueous solutions, which is often what we're going to be defining here, fall into this category of being a homogeneous mixture. So a solution is a uniform mixture, and that uniform mixture does not have to be a solid dissolving into a liquid, but it can be things like a gas dissolving in a gas into a liquid, and many other combinations that we'll discuss here in a moment. When defining a solution, there are two components to a solution, the solute and the solvent. The solute is the substance that's being dissolved, and the solvent is what's doing the dissolving. So oftentimes, whatever you have less of is the solute, and whatever you have in a greater abundance is the solvent. So in the case of making like salt water or sugar water, the sugar or salt, that's what you are attempting to dissolve. That is the solute, as where water is the solvent, what's trying to do the dissolving. Pop is another homogeneous mixture. The carbon dioxide in the pop is what was dissolved through pressurization to make carbonation, and water was, again, the solvent, what is doing the dissolving. In both these cases, water was acting as a solvent, and this might be a poor reflection on solvents. Water is known as being the universal solvent, but it doesn't mean that's the only thing that dissolves. So there can be many other solvents. Water is just a very common one. So when we distinguish a solution, we have to compare it to other types of mixtures that we can see in chemistry. So we can have homogeneous mixtures and we can have heterogeneous. And the two types of homogeneous mixtures or homogeneous include the aqueous solution. I'm just going to refer to it as solution and not say the word aqueous, and colloids. The one thing they again have in common is the homogeneous appearance. They're uniformly mixed, and that's because their particles are small enough that they're not able to make them distinguishable amongst what it's mixed in. So places you've crossed paths with an aqueous solution is things like salt water. Again, you can't see the salt dissolved within the water. Vinegar is consistent of acetic acid dissolved in water, diluted down with water. So again, they're uniform and they can't be seen. So we are in the same boat with a colloid because it's, again, also homogeneous, because yes, the particles in size are a little bit larger, but they are still well dispersed and not being able to be distinguished. So how we separate these two from one another is through the Tyndall effect. If you have ever been the driver or passenger in a vehicle going in a foggy set of conditions, you may have tried to put your brights on. And the thing you would find is that the brights or your high beams on your vehicle are a very bad choice to make, or bad selection to have in your light setting, because of the Tyndall effect. The particles are big enough in a colloid, but too small to interact with the particles that make up a solution. So as the photon, the light beam, collides into the water that's suspended in air that makes fog, it scatters it. So the Tyndall effect is the scattering of light, and we see that specifically with colloids. We're going to see that with suspensions, but the distinguishing factor here is that suspensions are large enough particles. They have other things that make them stand out. And so if we are looking at something and we're not sure, is it a solution or is it a colloid, we usually shine a flashlight or a laser beam through it. And if we see the light beam show up or the laser beam show up, we know that it's interacting with particles larger, meaning it has to be a colloid, not a solution. Suspensions are heterogeneous. So again, those are easier to pick out of a lineup. The particles settle out with gravity taking over time because they're large enough to, again, settle. So a lot of food products like orange juice, that tells you to shake well before pouring glass. Salad dressings often have to be shaken up before used as well. So a lot of food items and some drink items, and then some medications even, require mixing because they are suspensions. As I mentioned, a solution, again, contains something dissolved in something else. Well, again, we typically think of this example here, solid with a liquid, where salt water, where you took sodium chloride, mixed it with liquid water. But solids don't have to dissolve into liquids. Other things can happen as well for solutions to form. Gases can dissolve within a gas. The atmosphere is a really great example there, where nitrogen is the primary component. That is the solvent. And all the other gases in it would be the solutes. That's what's being dissolved. Again, carbonation comes from carbon dioxide being dissolved into liquid water. Alloys are a solid dissolved into a solid. So brass being an alloy mixture of copper and zinc is another type of solution. And then a liquid within a liquid includes things like antifreeze. So when it comes to determining solutions, the big thing that decides how much is dissolved is a property called solubility. So solubility is how much of that solute, again, like salt water, salt is the solute, is able to dissolve in the water, the solvent, at that specific temperature. So when defining that, one of the variables that, again, control the amount is temperature, and we'll go into a couple of others. We find that there is a difference in how well solids dissolve versus how well gases dissolve with an increase in temperature. And you may want to sketch these two graphs into your notes. But what we find overall is that when you increase temperature with solids, we get this nice positive slope. The warmer it is, the more it wants to dissolve. Think about coffee. If you have an iced coffee or an iced tea versus a nice hot cup of coffee or a hot cup of tea, that hot water has more kinetic energy. And so that is an increase in being able to dissolve. Gases, however, do the opposite. Gases have a negative slope. So the other thing we can do is look at a solubility chart and make inferences on what is a solid versus gas because of the direction of their curves. So solids have positive slopes, gases have negative slopes. Doesn't matter how positive or how negative, but we can kind of make an inference there on what would probably be in which of those two states of matter. So gases, again, the more warm it is, that gas, like carbonation in a pop, is going to give that carbon dioxide more kinetic energy, and it's going to want to go ahead and come out of the solution, especially as soon as you open it, taking pressure off of it because of the sealed cap or tab. Pressure applies only to gases. Doesn't matter how much you pressurize or remove pressure, that doesn't seem to influence how well something dissolves if it's a solid, but gases definitely feel the change in pressure in terms of their solubility. We find that when you reduce volume, okay, that is because of an increase in pressure, this is going to result in more collisions. Okay, if you think about these are moving around, more of this is going to ping pong and collide with the solvent, which we can maybe assume is water. The more collisions, the more it's going to want to dissolve in. Pressurizing leads to more gas dissolving. As where if we take that pressure off, meaning it has more volume, that gas is going to want to more readily escape and less will be dissolved into that solution. The last variable that controls how well something dissolves is the nature of the solute and solvent. So we know that if we put oil and water together, we know they don't mix. And it's because of this phrase, like dissolves like. So polar or ionic solutes like to dissolve in polar solvents. And so water, like I said, is a universal solvent that it dissolves just about anything because a lot of materials are polar and ionic, and it can even interact with things that are nonpolar. Something like gasoline or vegetable oil is not going to be able to, say, dissolve salt because salt is an ionic compound. So based on going way, way back to chemical bonds and how well or how poorly electrons are shared, that can decide if and how well it is going to dissolve something. And this is not a topic we're going to really dive into with the amount of time we have remaining. So as a chemist, if I'm trying to produce a solution, one of the things I want to consider is what can I do best to make my solution? And oftentimes it's a solid in dissolving into a liquid. So agitation, and I'm not talking about like a feeling here, but rather agitation as in shaking or stirring, we find that when we shake or stir something, that increases the rate at which solution is formed. Because the more motion you have, you're going to increase the contact between solute and solvent. The more they come in contact, the more readily it's going to make that solution. Again, if you think about making chocolate milk or Kool-Aid, it's not like you add those things to your water or milk and then walk away. One of the things you probably do first is stir it up. Okay, so the next thing that influences the rate of dissolution is particle size or surface area. Here we have, this could represent like a really large grain of salt, and these little dots here are representing the contact between that and a water molecule. So here, if we take and break this cube up, we find that there is more area, greater surface area for these collisions to happen. And so we find that the more surface area you have, because you have a smaller particle size like granular sugar or granular salt versus a sugar cube or rock salt, is that this is going to turn into a solution much more rapidly. The last factor is temperature. Again, think about temperature. It's a reflection of amount of energy. So the higher the temperature, the more kinetic energy, the more collisions, the faster it's going to dissolve. Okay. So as a chemist, the best way to make a solution is that I want to use water that's either at least room temperature, if not warm, versus ice cold water. I want to go ahead and try to grind up my solvent with or solute using a mortar and pestle if it's kind of lumpy. And the last thing is to stir it. Again, not anything that's really groundbreaking here. The last thing that this topic works on is some terminology called saturated, unsaturated, and supersaturated solutions. A saturated solution is like Goldilocks and the Three Bears. This is where it's just right. This contains the absolute correct amount of solute, again, what you're trying to dissolve, into a solvent at a very specific temperature. So here, if you're at room temperature, we can assume that's around 72 degrees Fahrenheit. There is a specific amount of sugar that you are able to dissolve in this glass of water. Okay. If you change the temperature, you change the solubility. If you increase the temperature, you'd be able to dissolve more sugar. If you lower the temperature, you would be able to dissolve less. But saturated is the just right conditions. If we don't have enough, which if it's like Kool-Aid, you would feel like it's kind of weak tasting Kool-Aid, kind of flavorless, and that it's holding less solute, less sugar, less of the Kool-Aid powder than the maximum. The thing with unsaturated is if you go to add more to it, you would find that it dissolves. If it was saturated and you added more Kool-Aid powder or more sugar, you would find that it would settle out to the bottom. And so you would have known at that point it was already at the saturation point. Lastly is supersaturated. And so the one thing by doing the PowerPoints, you don't really see the little videos with these. If you want to look up something called hot ice or sodium acetate, you can see some really cool examples of what's called a supersaturated solution. We can create what's called a supersaturated solution by heating it up and dissolving X amount of grams of the substance and then cooling it down. As long as it's not disturbed, it will hold more solute than it should be. When you watch the videos with hot ice in it, for example, a disturbance happens. And so here there's a little grain of this sodium acetate. And so what it does is it makes it crystallize out. And that's part of what we're going to investigate in our lab for this unit. So from there, we have what's called saturated, again, unsaturated, supersaturated, and we can look at what point is saturation on the graph. So one of the things you may want to color code is saturated is the line. So this can be whatever. I'm not sure what the substance is, but every place along this is, for example, this is 40 degrees Celsius. It can hold approximately, I would say maybe 98, 97 kilograms of this salt per 100 kilograms of water. So the thing that's important to notice is that this talks about a specific amount of water. You can't just have one drop of water and dissolve 98 grams. And if you had a whole Olympic-sized pool of water, you would be able to dissolve way more than this, okay? And we're going to see that here in a second with our questions. But what I'm really looking at with this is where do we find saturation point, unsaturated, and supersaturated. So this whole line is saturated. If it is unsaturated, every point below the line here, so everything I'm kind of going over here in orange, everything below the curve is unsaturated. The opposite is true, is that if we are above the line, we're looking at supersaturated. So everything above here is in the supersaturated solution region. Okay? So what we're going to do is use this information plus a few other pieces of info from earlier in the notes to look at a solubility curve. Okay, so these are the questions, but to be able to answer them, you need to be able to look at a solubility curve. So one of the things that I want to point out, and let me kind of adjust this so we're looking at the whole thing. There we go. Is that when we look at the graph, what we see here is that the x-axis is in degrees Celsius. And so we can see an increase in temperature. And then here on the y, it's solubility. The thing is, it's saying this is how much grams of solute, these are all solutes, so different lines for different materials, can dissolve if you have 100 grams of water. Again, that 100 grams will be important. As we take a look, this first question just wants us to know, is this saturated, unsaturated, or supersaturated? So it says we have 20 grams of KNO3 and it's at 20 degrees Celsius. So what I do is I find 20 degrees Celsius and 20 grams. This is how much of this KNO3 I'm trying to dissolve. Well, if you take a look, this line here identifies the potassium nitrate, this whole curve. 20 grams at 20 degrees Celsius is below the solubility curve of potassium nitrate. So since it's found below, this is unsaturated. Okay. If we change the conditions, so if we have 40 degrees Celsius and we're still trying to dissolve 20 grams, are we at, above, or below KClO3? Again, this is where 40 and 20 cross, and here's the line, the slope for KClO3. We can see that this quantity at this temperature is above the line, therefore this is supersaturated. Lastly, we have 90 degrees Celsius and we're trying to dissolve 10 grams of ammonia. We see that it crosses exactly with the line, so that means it's right on point. This is the right amount that you are able to dissolve. This is a saturated solution. Okay. So let's look at the rest of the examples that go along with these questions. B asks, how many grams of sodium chloride can be dissolved in 100 grams of water at 90? So we're looking at, to make a saturated solution, how much should we add? We know that it's being done at 90 degrees. I know that it's per 100 grams of water, so that doesn't change how I solve anything. And again, I'll explain more of what you do later. And we're talking sodium chloride. So we find 90, we go up to where it crosses with sodium chloride, which looks like it's happening at 40 grams. So you are able to dissolve 40 grams of sodium chloride, and after that, it would not be able to dissolve and it would settle out to the bottom. Here we have a saturated solution of KCl3, potassium chlorate, is formed from 100 grams of water. Again, our graph is in 100 grams of water. We don't have to do anything in our thinking. It says the solution is cooled from 90 to 50. How much of it's going to precipitate out? Well, we know that when something cools, it's not able to hold as much. Solubility drops. So what we need to first determine is what is solubility for these two temperatures. So we find 90 degrees and KClO3. And that crosses, it looks like, KClO3 is here. So it looks like it's approximately 52. There's a little bit of estimation to this, okay? So you just want to ballpark it, and this can hold about 52 grams. Well, if we cool it to 50, and we see where it crosses with KClO3, at this point, it can only hold about 21 grams, okay? So if we can originally hold 52, at this point it can only hold 21. What we do is just subtract these two, and that's how much is going to settle out. So 31 grams is going to settle out because solubility decreases with the decrease in temperature. Here in letter D, it's just asking which substance is most soluble at 10 degrees being the value here, and we're looking at which one can dissolve the most. So that's going to be your highest substance at that temperature, which in this case looks like potassium iodide. Right? Last two questions. In letter E, it asks if 120 grams of potassium chloride is dissolved in 100 grams of water at 80, how much will remain undissolved at the bottom of the test tube? So what we really need to first figure out is we are at 80 degrees and we have potassium chloride here. At 80 degrees, it can approximately hold 51 grams of potassium chloride to be saturated. So at 80, it can hold I think I said 51. Yep, 51 grams, okay? Well, we really put 120 into the test tube, so we want to know how much should be sitting out. So kind of like letter C, we're going to just subtract. We're going to take 120 grams that we add, subtract out the 51 that it's able to dissolve to make it saturated, and it looks like about 69 grams of the potassium chloride is going to be sitting at the bottom of the beaker here. Okay. Letter F asks how many grams of ammonia can be dissolved in 200 grams of water. So this is looking at a different quantity of water. So based on my graph, I know 90 degrees crosses ammonia at 10 grams. But that's 10 grams per 100 grams of water. Okay. So at 90, it can really hold 10 grams. So that means if we double the amount of water, we should be able to double how much it has. So it really can hold 20 grams when we have 200 grams of water. If this was really 50 grams of water, we would have taken that 10 and divided it by 2 because we cut the amount of solvent available. So however you influence the solvent, since this doubled, you do the same thing to your solute. So we doubled the solvent, we doubled the solute to get 20 grams. And that is a solubility curve.